welcome to Numerical Ship and Offshore Hydrodynamics. So, today we are going to cover this following concept. We start with the basic introduction of the course, followed by the discussion on different problem statement, and then we are going to discuss some different solution approach. Of course, there are a lot of solution for this type of problem, and finally, I just outline the overall course structure. Okay. And these are the keywords that you are going to use while searching this video. Well, let us start with a video. Now, you see the ship is moving in a calm water, and you can see that there are waves actually created by the ship because the ship is advancingly forwarding, and then in the back side you can see there are some waves, right. This is typical problem wave resistance. Now, you can see the ship start oscillating, and then there are another type of waves is coming, which is called the radiation waves, which is coming because the ship is oscillating inside the water. Now, you see now what happening, the waves hit the structure, and because of that you can see there are large motions of the body. Now, you see now this phenomenon is very complicated. Why? Because this phenomenon, let us see again, in the last part of this video, you can see here this is a very complex phenomena. Why it is complex? Because it is combination of so many different types of waves. One is when the ship is coming forward, in back side you can see the waves, ship is oscillating, because of that some wave got created, and then finally the wave is the instant wave is hitting the body, and because of that you have a large motion. Now, in this complex scenario, what is seen in this video, at this particular time what is happening, all sort of waves are acting on the ship, and then because of that the ship experienced large amount of forces. But then how to compute these forces is not a very easy task, because you really do not know what type of force is coming because the ship is moving forward, what type of wave is coming because the ship is oscillating, what type of wave force is coming because the wave is hitting the structure, right. So, it is very interesting of course, but pretty complicated as well, right. Now, this course is not possible to cover everything, but certain amount of things we are going to cover, but let us see that what different type of things we can do. First, on this we can find out the floating body problem. It means that ship or offshore structure is floating on ocean, and then waves hitting, then what is the interaction, right. It is very important for the offshore structure problem. It is very important like for semi submersible structure extracting the oil from the ocean, that time this problem become very important. Now, second one is that when the ship is moving forward, right, at that time also there are in floating body problem you have the waves that but the body is not moving, but because the body is moving, then you have another type of forces coming into the picture. So, therefore, it becomes a forward speed problem, which is more complex than the floating body problem. Now, these two major things that actually we are going to cover in this course. However, there are very classic two problem also and also very popular, which is wave resistance problem and then flow around a propeller. However, you need little bit of viscosity comes into play in these two problem, and this is now not the scope of this particular course. Here we mostly concentrate on the floating body problems and then forward speed problem. Okay. Now, this is a very interesting picture. Now, you see that why this is so complicated. Now, if you look at here, you can see this is the first time actually when actually we are going to start this process, right, and it started with the hydrostatic. That means, in calm water nothing is moving, there is no waves, and we try to find out what is the forces. Now, you can see that the time is 2500 BC. Now, you see it is not a continuous graph. Okay. this is basically some points actually are extracting. Like you can see here, this axis is called the velocity, but it is not a continuous axis. I just pick some point here and just there is some meaning of this particular point. Now, here this is velocity, that means, if I advance from here, actually I am in getting the velocity, the ship is moving forward. Now, this side, this axis is basically the sea keeping, or we can call is the waves. Okay. So, now and if you look at this top axis, this one, this basically our complexity or non-linearity. Now, let us see where we are. Now, this particular point is basically it is in this axis. Now, here at this point there is no velocity, there is no waves, because this axis is also 0 0 0, there is no velocity, there is no waves, and there is no non-linearity, and we call it the hydrostatic. And this is how it started in 2500 BC. Now, this point particularly, it has no waves, of course, because it is in this axis where wave is 0. So, here you have no waves, and then it is basically the ship is moving in a constant speed. So, this is basically when the ship is moving in a constant speed, and we call this as a typical wave resistance problem. Now, let us go this side. Now, this side basically there is no velocity, therefore, ship or structure is not moving, but you have waves. So, typically this is called the floating body problem that I discussed in the last slide. Okay. Now, let us move little bit up in nonlinear side. Now, you can see here from 2500 BC, actually it is this takes that much of time to solve this problem, 1980. So, you can see that we need almost 2000 years to come from hydrostatic for this second order diffracted problem. That means, even we do not introduce the speed, the floating body, and then the floating body problem, even the linear problem, where actually we solved in 1970. Now, you can understand how much complex it is when you started from the hydrostatic to this particular level, right. Now, let us see this point. Now, after this point, actually till this point we did not consider any acceleration of the body. Now, you know that if you do not consider acceleration, then the ship is moving in linearly, right. The ship cannot take a turn. So, for that you need acceleration. So, here ship can take a turn, and we can call this a classical maneuvering problem, right. However, still we do not consider any wave, right. So, now we can standardize, even you can see the linear wave resistance, where we really do not consider the waves, only consider the forward speed, it takes 1908. So, we understand, right, that how much effort is required, right. Anyway, now let us take this part. What is this point? This point is basically you have waves and you can have also velocity, right, because till this point we consider the ship is moving with a constant velocity. Now, this point ship is moving with a constant velocity, and this we call the forward sea keeping problem. So, this point also it is important I am writing, because this is the major focus of this particular course. We can call this forward speed problem. Okay. Now, there are so many nonlinear side, let us go a little bit. Now, here it is linear wave resistance problem. If you go up this point, if still we do not consider the waves, we can call the nonlinear wave resistance. Now, here actually we can call the added resistance, which is nothing but the you can say nonlinear part of the wave resistance problem. We can move little bit of nonlinear side. Now, here let me see that we are going to achieve. Actually, our goal is to achieve this point, right. Here we have no wave, no velocity, no nonlinearity, the waves are, and here the point where we have everything. We have the velocity, we have the nonlinearity, we have the nonlinear waves, right. And this point actually yet to achieve. So, we can understand we started in 2500 BC and still we are not getting into the complete solution. The closest solution you can see, although it is this one, which is called the MEL method. We are going to discuss this all later stage of this course. In this particular situation, what we did basically, we are considering, we do not consider the acceleration of course, we consider only the without acceleration, then body is moving forward without acceleration, and you can incorporate the nonlinearity in the sea keeping problem. Okay. And then very interestingly, we do not even achieve this point, we have not even achieved this point. What is this point? Here ship has a acceleration under the waves. So, that means you can see the maneuvering where that there is no wave. So, it is the acceleration without considering there is a wave. Now, here we have considered the acceleration and also we are considered the linear wave. Even now this is become a huge problem for us. We do not have very consistent solution for this. However, our course mainly focusing on this green to green circle. This is one and another one is this one. Okay. Now, let us see that what level of assumptions we are making to come to this particular stage. Now, here we have general 3D incompressible constant, this is the general problem, like we consider the viscosity and we solve the Navier-Stokes equation. So, this is the most general situation. Now, what we did is from here we actually come here, let we do not consider the viscous term, we only consider the inviscid fluid flow, right. So, we consider the inviscid fluid flow and also we do not consider the rotational flow, right, and only we consider the irrotational flow. See, you have two level of approximation from here. The starting we have started with the Navier-Stokes solution which has viscosity and then we do not consider the viscosity and then we do not consider the rotational also, rotational flow we consider the irrotational flow. And also there also again you can see here further making the approximation. We do not consider the infinite fluid flow, we consider the free surface flow. That means, we consider the ship not inside the ocean, not the middle of the ocean, or it is not submarine, right. It is basically ship which is floating on ocean surface. Now, under this also you can see there are hell lot of solutions. First is linearized free surface, then linearized free surface boundary condition Dawson type solution, we have nonlinear and we have the blending techniques, right. Under that we have 4 solutions. However, we are mostly interested on the first one, which is the linearized body conditions, right. And from that, even that also we can have the 4 solution. We have first order thin ship theory, we have slender body theory, we have Neumann-Kelvin problem, we have body exact conditions. Now, from there actually most popular one is basically the Neumann-Kelvin approximation. However, still in this course we try to address this problem as well, where we can do some kind of nonlinearity into the solution. Okay. Now, from this actually we can understand that what level of approximation we need to do to address this particular problem. This problem appears to be very simple. It is the ship floating on a water and then there is a waves and wave is hitting to the structure, because of the structure start oscillating, because the structure start oscillating, then you can have some kind of waves, right. And this all this mechanism we try to address. It appears, when you see if from offshore, you can see some ship and wave is hitting, and even when you go like oceans and we can just go for bathing and all inside the ocean, we really do not understand like what complex phenomenon is going on, right. However, if you want to solve this problem numerically, then we cannot solve as it is, we have to make lot of approximations. So, particularly we need to understand what level of approximation we are making, and because of this approximation it is not possible to address all sort of problems, right. Sometimes nowadays what happened that let a lot of somebody working in some kind of industry, right, and then you have lot of softwares, available softwares with you, and therefore, somebody asking you to run the software and try to figure out like what is the response of the vessel to give a proper design of the vessel, what is the design load you need to calculate all these things, and therefore, you run the software. However, you do not have enough knowledge or enough understanding on the approximations. Then what happens after some point of time, you can find some results. Of course, if you run a software, definitely you are going to get some kind of results, and then really you do not really understand whether this results is actually realistic, this result is meaningful, you really do not know. Why? Because you do not have the background knowledge and you do not have the knowledge of the approximation. So, what happens sometimes your software gives some erroneous results, and that might represent kind of weird physics, and but since you do not have the knowledge of the limitations of the softwares, and when the software may go wrong, you really do not have an idea, you keep on insisting the wrong physics, and what is the outcome of that? Your design is faulty, and then that actually very dangerous, because the load you are calculating based on that particular physics, that again fail, right. So, therefore, we have to understand, like you can see over here how much approximation we are making, and really if you go into the ship and in a ocean, nobody is going to tell you that it is basically a linear waves, or let mean how many of you go to the ocean and find the waves are basically harmonic? Nobody, right. Even if a kid, if you ask a kid to draw a waves in a cartoon also, mostly they draw like this type of waves, kind of this irregularity is always there, right. However, under this linear assumptions, we are approximating the waves are harmonic, the response are harmonic, right, and then we are ignoring some kind of nonlinearity in the process. So, we are making approximation, of course. But however, even if we make such approximation, still our theory holds, and then this all these calculations, all these numerical methods are still meaningful. Okay. Now, it is very interesting slide actually. Here year wise, actually I am trying to find out that where we are standing. Now, you see that in 1970 onwards, that first time the strip theory actually and 3D positional theory is developed, and this is the first time actually we are really try to attack the problem, and still now it is 2022, still these methods are valid and very popular in industry level, particularly the strip theory. However, during 80s and 90s, normally in before the 70s, only the 2-dimensional methods are very popular, like strip theory, slender body theory and other type of theory. Now, during 80 to 90, the 3-dimensional potential theory become very popular and people started using it. Okay. And this is of course based on some assumptions of the irrotational, and then you have to find out some velocity potential, all these things we are going to discuss later on. However, from 90s people are try to address this problem with the help of CFD. and we are having the Rans based solution, but it is you can see the Rans steady, that means their solution is not particularly for the sea keeping problem, mostly the solution is for wave resistance problem. That means, ship is moving in calm water, then what type of force is acting on the ship. So, such problem actually they started addressing in during 1990s, and then in from 2000 onwards actually we try to address little bit of non-linearity into the solutions. Okay. So, what kind of non-linearity we introduce? We introduce the wave non-linearity, then we consider the wave is not harmonic. Okay. So, wave is non-linear waves, you can approximate with lot of theories are available. You can approximate complete non-linearity, we can approximate second order non-linearity, fifth order non-linearity waves, so many things we have started. However, most of the time that response of the vessel always assumed to be linear. So, what they do is they assume the waves is hitting to the structure, that waves is a non-linear waves. However, the response of the body is still linear. That means, if you look at that video where we can see that body is moving. So, the body is moving, we should consider that also be a non-linear, but we do not do that. So, the wave created because of the body is oscillating, that wave should be non-linear, but we do not consider that to be non-linear. Only we consider that wave which is hitting to the structure, that is non-linear. So, these things again still we are working on this particular problem, and still we do not have very satisfactory solution for that also, but we are going to discuss this also. And finally, as I said that our ultimate aim to achieve the unsteady Rans solution, that means we consider everything. We consider our ship is moving with acceleration, we consider that waves is non-linear, and we consider the all other waves created by the ship, that also non-linear. We can take a turn, we can do maneuvering, we can do sea keeping, we can do everything. So, this we need to achieve. Okay. So, now as you can see here, we are here, I mean this point, still it is in a 2022, somehow we are here, and I hope that after this course we are some people will try to solve this problem as well. Okay. Now, let us see that what actually we can address for this particular course. So, first we started with floating body problem. Now, here we consider everything is linear, the wave is linear, and also the response also linear. And then after that actually what we are going to discuss is basically a time domain solution. Now, in time domain solution, this again everything is linear. Okay. In third, we are going to address the forward speed problem. So, what is happening that this also in time domain. Okay. And then number 4, we are going to discuss some kind of nonlinearity. At least we can consider the wave is nonlinear, maybe not the responses. And finally, we are going to discuss something called hydroelasticity. Now, what is hydroelasticity? We are going to discuss in the next slide. We have that some video of the hydroelasticity, and then finally, if we get some time, of course, I wanted to of course do something something extreme waves. Extreme wave situation. So, here actually we can address something called the green water, and sometimes we can have the slamming. Okay. So, what is the green water and what is the slamming, definitely we are going to discuss in the in coming days, and at the end of this of course, the course. Now, let us see our ultimate aim to develop a software which address the fluid structure interaction problem. At least let us take a linear wave, and then let us take the response also linear, and also let us take the structure is not rigid, the structure is elastic. Let us see if you assume the structure elastic or flexible, what happened. Now, here you can see that the waves is hitting to the structure and then structure oscillating. Now, if you look at carefully, this structure is not behaving like a rigid body, and what is happening for the large floating structure. The structure is no longer behave as a rigid body and structure behave as a flexible body, and actually this becomes more complex to solve, but this phenomena is very interesting and very important also. Sometimes we really do not realize we are carrying some 400-meter long vessel and we are going in the middle of the ship, and suddenly that all the responses are small. We are very happy the wave condition is absolutely normal, there is no extreme waves, okay. And suddenly what happened, the ship breaks due to some high bending moment or whatever the cause. And that time actually it happened in 2013, right, when this hydroelasticity started become very popular. There is some very large ship just going inside the ocean, and suddenly it breaks, and people find out because we really do not consider that at 400-meter long ship is no longer behave like a rigid body. So, in this particular course also we are going to address this. Okay. So, this is that our final aim. We are going to model a numerical method, and this is our final aim. Okay. So, with this let us stop today. Thank you.